So our fourth speaker today is Dr. Taija Torvela. Dr. Taija Torvela began her academic career at Abo Academy University in Finland, where she studied for a PhD, the four-dimensional evolution of a shear zone in a Precambrian basement. After a brief time in industry, conducting exploration for manganese minerals and as a structural geologist perceiver in Finland, Taija completed a 2-year postdoctoral fellowship in which she was involved in the development of the virtual seismic atlas. Taija was then appointed as a lecturer in structural geology at the University of Helsinki, and in 2012 became a lecturer at the University of Leeds, where she is now a co-leader of the Ores and Mineralization Research Group. Taija's main research now focuses on deformation processes at varying scales and how this affects ore mineralization, and the use of structural geology in mineral exploration to secure metal resources for the green energy transition. Thanks for agreeing to give a talk today, Taija.
Great, thank you very much, Sam. I'll just share my presentation. Here we go. That seems to be working. So, yes, thanks for everybody for coming to this talking, and thanks indeed to the organizers as well. Very interesting conference it has been, and well organized. So well done with all that. So yes, my talk is indeed going to be focusing on the key roles of metals and also geoscience in the transition to low carbon future. But before I start my actual talk, I thought I'd just give you a little timeline of my career, not particularly because I want to talk about myself, but it's just that I talk to my own students, and I know there's a lot of students in the audience here. I talk to my own students, and quite a lot of them get really stressed and worried about the future, and not everybody has that sort of clear idea of what they want to do in the future. That, okay, this is what I want to do, and directing their efforts onto that. I have that really clear vision as to where they want to go. So I just thought I'd share my own career path, which is not straightforward. As Sam mentioned there, I've been in industry, I've been in academia, I've been doing all sorts of things. And just that, hopefully that reduces the stress for some people. It's going to be fine. So I started my geoscience career in 1995 when I started my master's. And those days we didn't have, in Finland, there wasn't a separate bachelor's program. It was just a straight master's thing. And during that time, I spent 2 summers working as an exploration geologist in Lapland diamond exploration. It's not as glamorous as it sounds. It basically involved shoveling loads of till into big bags and sending them for geochemical analysis. So I did that for 2 summers. It paid quite well. It was good fun. And then I got a research internship at the university where I was studying as a part of my dissertation project on contaminated groundwater and how we can use certain geophysical methods to detect and map out these contaminated groundwater areas. Graduated in 2000, became an environmental consultant. So I worked for this consultancy looking into remediation of contaminated soils. So project planning, project remediation, project overseeing those projects on site. But then I thought, actually, I would want to go back into research because I quite enjoyed that process of really drilling into research problem and getting to the bottom of things as much as possible. So I went back to the university. I also decided I want to do rocks rather than sediments, so I chose structural geology as my main topic because that was something that really interested me, as well as environmental geology. Those were the 2 things that really interested me when I was doing my master's. So I did that, finished 2007, spent a year looking for volcanogenic massive sulfide deposits in Finland. Then I spent a bit of time as a structural geologist for ProSiva, which is the organization in Finland who is responsible for nuclear waste deposition, and then finally postdoc in Aberdeen, like Sam mentioned there, then lectureship in Helsinki, and now I'm in Leeds and having a terrific time, as you can see. I mostly teach on MSc structural geophysics, and I was also program leader of that for 4 years. But the key message here then indeed here is don't panic. If you don't know exactly what you're going to do yet, it's not mission critical in terms of getting there at some point. As you can see, I've been doing all sorts of industry. As a career, I've been in and out of industry, academia several times, and it's all going to be fine. So don't worry about it too much. Just do something that interests you, and when you do your studies, and opportunities will arise. In terms of my own research, like Sam mentioned, I do structural geology research. I've got 2 strands really. I do melts and deformation and structural geology of ore deposits, particularly gold in Caledonian belts of Scotland, Ireland, and Newfoundland. But I did not really want to talk about my research today, simply because I think this platform and this theme of the conference gives the opportunity to take a broader view into geosciences and its role in society, particularly with the view of energy transition and how we as a community can contribute to that from resources perspective. And indeed, this is what it is all about: global warming, energy transition, and the target, or rather the limits that have been set for the global warming in the most recent climate summit COP26. Quite an ambitious target, 1.5 degrees C. It's been tightened from the previous target, which was maximum 2 degrees set in Paris in 2015. And what that then, of course, means, as I'm sure everybody knows, is that if CO2, excess CO2 in the atmosphere is seen to be the main cause of global warming, decarbonization is key in trying to limit that global warming to 1.5 degrees, or preferably less. Decarbonization obviously then meaning that we have to stop pumping anthropogenic CO2 into the atmosphere. And that then means, of course, as I'm sure we all know, that we have to drastically change the way that we produce energy globally. So we have to stop burning coal. We have to transition away from combustion engine-based transportation, home heating, industry, etc. So electric vehicles, planes that are not burning kerosene, etc., etc. These are all key components of that decarbonization. And the thing is that this needs to happen really quickly. So various smart people, scientists, have done a bunch of calculations to estimate how fast we need to transition into low carbon energy production if we want to keep the global warming within 1.5 degrees. And the magic year is 2050. So we do need to transition into energy production that is not dominated by hydrocarbons, so mostly renewables, by 2050. So less than 30 years. That's a short time in the scheme of things. So what do we then need to do in practice to significantly reduce the global reliance on hydrocarbons? So energy production is, of course, key of that. We have to build up the global energy mix that is more sustainable, low carbon form of energy generation. So we are talking about solar power, wind, tide, geothermal energy, hydroelectric. Hydrogen will be an interesting thing if it becomes more energy efficient to produce, more widely available. So that will certainly be quite probably a very important part of the more sustainable energy mix. But in addition to the energy production and generation, you also need infrastructure to then transport and distribute that energy to the end user, be it industry or just us common people trying to get about our daily lives. So there's a huge need for cabling, new transformer stations, batteries. Batteries are not important only for our cars and cell phones. We also need batteries as a really critical part of the electricity grid for the electricity distribution. And then indeed the end user technology. So we're talking electric vehicles, home heating solutions. So the majority of UK homes, as you probably know, are heated by gas at the moment. So that needs to change. And yeah, so all sorts of industry applications. So we need to move away from relying on hydrocarbons in all these sorts of parts of the society. And I'll just take a bit of a historic view to this. Any technological advance and move to a new stage of society sort of demands more resources, new types of resources. So if we go from simple horse cart scenario, for example, which was mainly about just muscle power, bit of wood and leather, maybe bits of iron and bronze, go to Victorian era and the rise of the Victorian train network and other similar applications. Suddenly, huge demand for steel, which is an alloy of mainly iron with bits of things like chromium, nickel in there, mixed into it to make it more durable. Suddenly there was a huge demand of steel, which then, of course, inspired the Industrial Revolution in part. Then moving forward to the 20th century, with people getting their own cars and stuff, and everybody was buying a new car, certainly in the Western world, and a combustion engine vehicle. Suddenly you need loads more aluminium, copper, cobalt, lead, zinc, cadmium, because of course not only the body of the car needs metals, you also need metals for the electronics and the components inside the car as well. And now what we're looking forward into the future, we're going to have to move away from these combustion engine vehicles into EVs, so electric vehicles, which also need different types of metals and more metals than a conventional car. And I put a little question here: how much more do you think that an electric vehicle contains in terms of copper, for example, compared to sort of conventional combustion engine? And the answer is 3 to 6 times more, just copper. And if we're talking about large vehicle like buses or lorries and stuff like that, we're talking teens, so easily 15, 16 times more copper wiring that goes into these things. So in addition to that, there's of course the batteries as well, which I'm sure you've heard lithium will be a really key component, or is a really key component in modern batteries, in addition to many other metals and rare earths, etc., etc. So there's an array of metals that are going to go into the batteries in these EVs. And then in terms of wiring and electronics, I already mentioned copper, but in addition, you need various precious metals as well. So yeah, again, an array of things that will need to go in. And then the energy transport and distribution bit, if I stay with electric vehicles, because I guess that's something that we can all relate to quite easily, not just that, is forecasted to use about 250% more copper in the next, well, less than 10 years. Because of the need to build more charging stations than we currently have and expand that charging network. So in addition to copper, we will also need aluminium, nickel, titanium, more steel, but plastics as well. Unfortunately, we're not going to get away from hydrocarbons entirely, because almost everything these days needs plastics, including charging stations. And then, of course, the upstream bit of it, so the energy production side. So just to take a couple of examples, your average windmill, a 250, 300 ton windmill, requires mostly steel, which is again an alloy of mostly iron plus various other base metals. You'll need various other metals for the turbines as well, cobalt, molybdenum, rare earths, etc. You need aggregates for cement and concrete. And again, unfortunately, you need 40 tons of plastic as well. And this does not include the infrastructure, the cabling to transport and distribute the energy that is produced in here as well. So huge amounts of resources are needed. Take solar panels, for example, photovoltaic cells for just your average household solar panel system, such as you might have on your roof. Half a ton of glass made out of quartz. You'll need some aluminium, copper again, and other elements, particularly silver, is going to be really, really important for building these cells. Silver is the reflective element that goes into these, so very important component. Again, polymers and infrastructure separately. And quite a lot of research goes into then trying to predict how much more do we need exactly in the future for various scenarios of how fast we want to build these infrastructures, these power plants, etc., etc. And this is from a report by World Bank in 2017. And there are many ways of looking into these things and calculating and forecasting, but they all point towards the same thing, that the demand is going to go up. These guys, they run various scenarios that they call 6 degree, 4 degree, 2 degree scenarios, with 6 degree scenario basically meaning that we don't do anything in particular, we just continue with the current projected rate of growth and adoption of green energy and technology. 4 degree scenario would be increase building the infrastructure and production a little bit more, and 2 degree scenario is the one that we should be looking at 1.5 really, but by in 2017 that was 2 degrees. It means that we have to build renewable energy production and storage distribution, etc., even more rapidly, i.e. trying to decarbonize by 2050. And that requires more resources. The faster you build, the more resources, the more is the demand for resources going to ramp up. So just for wind power, for example, there are various metals here displayed here at the bottom that are going to be needed for windmills. And here on the y-axis, you've got the percentage increase. Can I actually point to? So I don't know if you can see my pointer, but anyway, there's a percentage change here on the y-axis on the left-hand side. And these colored bars then represent different scenarios. So of course we want to look at these blue bars, which is the 2 degree scenario, so decarbonization by 2050. And you can see that the increase in the demand of these metals is predicted to be about 250% compared to what it was in 2017. Similar for solar power. Again, here on x-axis, you have the various metals that go into these things. On the y-axis, you have the percentage change, and we're looking at 300% increase in demand for these metals if we want to try and reach this 2 degree limit, or keep the global warming within about 2 degrees. It gets even more serious when you look at energy storage solutions, so basically batteries. Again, here in the x-axis, you've got the various metals that are needed for batteries. On the y-axis, percentage change, and we are talking about more than 1,000% increase in demand. as calculated by these guys. So it is really going to ramp up if we, like I said, want to try and reach this 2050 target. Things are already happening. So we are already building more renewable energy. So this graph here shows how the global renewable energy capacity changed in the past 10 years or so. And it's been increasing. And last year, there was quite a significant increase in renewable energy capacity, i.e. people built, or countries built and companies built more renewable energy production. So there was a nice big jump last year of almost a third of the global energy production. So that's great. So is that enough? If we keep this up, this is good news, isn't it? But actually, it's not enough, unfortunately, because global energy demand is growing so quickly that we are already struggling to keep up in terms of even maintaining the current percentage of non-fossil fuel based energy production. So even though we are building more, we have built more renewable energy production. This graph here shows that from 2009 to 2019, how the global energy demand in total changed. And you can see that the percentage of fossil fuels barely changed at all during that time, even though we built much more renewable energy sources. So that's not good news for global warming, is it? So the conclusion is that the building rate, so the speed that we are building these renewable energy resources is simply not fast enough to replace most hydrocarbon-based energy production by 2050. We really significantly have to ramp up the rate that we build these things. There are several complications, there's several limiting factors though. There are societal, economic, political complications in that. But one limiting factor, but potential bottleneck, is certainly availability of metals. There are already signs of that. I already mentioned copper, and I will talk about copper a lot more in a little while, but there are also signs that other metals might be looking a bit scarce as well. These things, go up and down. So some years supplies are better than other years. But yeah, there are already signs that there will be bottlenecks caused by availability of metals. And the problem is that we just currently don't have enough reserves and resources to cover that, that predicted future demand. So again, this is from the World Bank report. Just taking neodymium and silver as examples, the stippled line there at the bottom in both graphs illustrates what is the total current annual production for each of these ones. And again, they run various different scenarios depending on how fast we build the renewable technology, what sort of feasible technological advances we might foresee in the next little while that makes these things more efficient, etc. But whatever calculations they did and whatever bar you're looking at, they all show the same thing, that the current or the 2017 production and the rates haven't changed that much. It's simply not enough to cover the demand, the projected or predicted demand for these and many other, most other metals and elements. This is another research, a bit more recent, by Mahoya et al., 2019. They looked into current reserves, and there are some good resources these days. If you go, for example, to USGS website, you can find their calculations as to what are current global reserves for various metals. And at this point, I want to point out that mineral reserves in oil is a very, very specific term. It basically means something that is legally, economically, and technically feasible to extract. It's not just any or glittery rock. It has to be really something that you can economically extract and exploit. So, for example, USGS, they have a pretty good estimate as to what are the current global reserves for various metals. And this paper here then looks into that and looks into various possible recycling scenarios for things that we already have, plus then the things that we are currently mining from existing mines. And lithium actually doesn't look too bad, and manganese neither. But most of the other metals, we are looking at depletion of the current reserves by about 2040, so less than 20 years' time. So that's a bit worrying. I'd like to talk a bit more about the recycling bit, because you might come across this concept of circular economy, which is a really, really nice idea that we should be, and hopefully in the future, I generally hope that this will work at some point, that we can actually just reuse and recycle things that are already mined, that we have in circulation in the society, so that we don't have to mine so much new stuff out of the ground. So some topping up will probably be necessary. But unfortunately, we are not there yet. We're quite far off from actually being able to go into circular economy. And there are several reasons for that. Well, first of all, many metals are already efficiently recycled. So this periodic table here on the left has some color coding in there to show what metals are quite efficiently recycled globally. This is a global review, and which are less efficiently recycled. And most metals that we are going to need for energy transition, so base metals and precious metals, they are already globally quite efficiently recycled. So they are simply not available for new energy sort of production, building, etc., because they're already being used for something else. And maths don't add up anyway. Even if you could increase this recycling rate for, let's say, copper, which is commonly 70–80% of it is already recycled, that's not going to meet the demand if the projected demand increase for copper in the next 20–30 years is 300%. So the numbers just do not add up. Other metals, such as lithium, for example, they are not efficiently recycled at the moment. So if we want to do that, we need to develop relevant methods and develop infrastructure. And it's not easy to, for example, if I take batteries, and I'm not talking about AA batteries, I'm talking about car batteries and other sort of electricity grid storage batteries. They are much higher voltage, so they pose a safety risk in recycling plants. So they are not easy to recycle. That recycling also demands in itself a lot of energy, and there are also lots of logistical issues, because obviously these things are really, really heavy. So it's not an easy solution just to say, okay, we'll just recycle more. And another significant problem is also that most metals degrade when they are recycled, and which with each cycle they degrade more, because most plants are not capable of recycling the metals so that they don't incorporate lots of contaminants in them. They're just simply not set up for it. And most importantly, copper. Most recycling plants are not capable to produce pure enough copper that can be used for electric wiring, because electric wiring requires copper to be 99.8% pure, and most current recycling plants are simply incapable of doing that sort of, delivering that sort of purity for recycled copper. So that's not helpful. So conclusion is we simply can't recycle our way out of this. The numbers don't add up, and there are lots of complications in recycling as well. So if we do want to have any chance of limiting the global warming to about 1.5 degrees. We just have to mine more metals in the next few decades for sure. Well, then you might think, okay, well, let's just open new mines then, yeah. Again, unfortunately, it's not that simple. Exploration is really costly. It's very, very risky. And companies, they just simply don't invest until there is reasonable chance of getting their money back. So that means the metal price has to already be high, and which then, of course, means that the demand is already high. It's already going up. So the graph here on the right, it shows global exploration budgets versus metal prices. So that dark blue line there represents annual global non-ferrous metal exploration budgets, and you can see that it goes up and down. In the recent years, it has been going up, and it's been going up quite rapidly lately. And then the blue bars there, they represent exploration budgets. And you can see that broadly speaking, although strangely not in the past few years for some reason, but broadly speaking, the exploration budgets do follow the metals prices, but there's always a little bit of a lag of 1 or 2 years before the exploration budgets are really properly ramped up. And that's obviously a concern if you rapidly need more metals, but also it reflects very much the fact that exploration business is very risky, and companies just are reluctant to invest until they think they can get their money back. Another problem is that most occurrences, even if you do find something, you find some sulfides in macro, most occurrences will never be feasible. They will never be mined. They're just not, maybe the grade isn't high enough, maybe it's politically, infrastructure is not there, the country is not stable enough in terms of legislation, maybe there's a war going on. There are millions of reasons why, not only geological, but also political, financial, why most occurrences will never become a mine. So again, yeah. There's a little thingy here saying mineral resources are potentially valuable with the reasonable possibility of becoming a reserve, i.e. eventual economic extraction. Most occurrences will never be reserves or even resources. So the ratio is somewhere around 1 in every 1,000 discoveries. For some deposit types, 1 in every 2,000 discoveries ever actually become a mine. So the ratio of the chances of failure is really, really quite high. And last but not least, even if you do find something that is eventually going to work, it's going to take ages to actually open the mine. So for a typical mine, we're looking at a timeline from discovery to mine opening of more than 20 years. And it's almost unheard of to open a mine in less than 15 years from discovery. And there are several very good reasons for that. There are technical reasons that you have to plan how you're going to set up your mine. You have to understand your deposit before you even start excavating. You have to do a lot of drilling. And into that then becomes that question of investment and financing the whole project. It can take a long time to actually raise the resources because of this huge chance of failure at any stage of the process. And importantly, especially in the Western world, and quite rightly, there's environmental considerations that need to absolutely be taken into account. It takes a long time to make sure that the footprint of the environmental footprint of the mine is as small as it can possibly be, both in terms of contamination, but also in terms of how you respect local communities and take their needs into account as well. And these take really a long time to plan, and that's why it all takes a long time. So, and that's not great in the sense that if we need those resources in the next few years, and it takes more than 20 years to open more mines, then it's a bit of a conundrum. as the timelines are just incompatible, really. And in some ways, there are more worse, bad news coming in the sense that many metals are also getting harder to find. So copper is an example of this. So we have here on the right, there's a graph showing copper exploration budgets globally in millions of dollars. And then you've got these bars, yellow bars showing copper and reserves and resource and production. So basically stuff that is being mined or very soon is going to be mined. And then you've got these red bits of the bars which show deposits or finds that are very likely to become mines. And there's a worrying trend here that 2010 was a peak year in terms of exploration budgets. So the companies put a huge amount of money into exploring for new copper deposits in 2010 in particular, and they found very little in comparison to what had been found in the previous years and decades, even though they put massive amounts of money more into the exploration. So the picture is quite worrying in terms of what people are finding, even if they put money into it. So that's not good news. We need new innovations in how we approach exploration so that we can find more stuff. And yes, coming back to this, just reiterating as well that the demand of copper and other metals is only going one way because the energy transition is going to ramp up in the near future. And this is quite a nice graph illustrating that, again, taking copper as an example, but how the supply of the metal versus demand are currently seen as incompatible. So here there's a timeline in the x-axis at the bottom from 2020 to 2040, millions of tons of copper here on the y-axis, and there's a couple of things here. First of all, there's this red line here which represents the forecasted primary demand, so i.e. the demand that we are currently using just for the basic growth of the planet, population growth, and people getting out of poverty, you know, in developing countries, trying to get more onto the ladder of things. So that's just the basic demand, which is that red line. And this dark blue line here then represents the demand that is predicted if we want to ramp up building these renewable energy resources and infrastructure, etc., for 2-degree warming scenarios. So you can see that there's quite a big change in terms of that energy, copper demand. And these colorful bits down here represent, first of all, what's already been mined. So this lighter blue stuff down here represents current reserves, so things that are already being mined at present. Then there's this gray bit here, which represents mines that are just about to be opened, or they're forecasted to be opened in the next couple of years. And then there's other colors here, and the uncertainty that these projects will actually ever come into fruition increases as you go towards the orange bit up here. So there will be a ramp up, hopefully, in terms of how much copper we produce sometime in 2027, 28. But either way, even after that ramping up of production of copper, we still have a gap between the supply and demand forecasted in the next little while. So that's almost certainly going to be a limiting factor here. The mining companies, they do know this. Last year's exploration budgets already went up for all metals, including copper, and that trend is likely to continue this year, despite the for example, copper again, there is a current slight surplus in copper, but that's not going to last. Companies do know this, and copper prices reflect that. The copper prices are really high at the moment. So companies do know this, which brings me sort of to the last part of the talk, where I want to talk a little bit about how us geoscientists, so you guys, can contribute to the energy transition positively by helping out with this. Because the mining companies and exploration companies, they need geoscientists, as simple as that. And they need geoscientists in all parts of the process. It's not just the exploration, it's also the mine development and mining itself. All mines have mine geologists who oversee the planning of the actual mining operation, try to understand where the grade is and how to best target that. But in addition, there's geoscience roles also in the environmental side, for example, both in the planning stages, but also during the mine operation. You have to monitor the environmental impact, taking soil samples, water samples. You have to, after the mine close, there are roles in reclamation and remediation of the land, and then further into sustainable land use after the mine life. So the geoscience roles are present in all parts of this cycle of a mine life. So, okay, maybe I enthused you a little bit, but again, if you still don't see a clear career path open ahead of you, don't worry, don't panic. But if you started thinking, okay, well, maybe this might be something that I could consider. It's not a bad thing to start thinking about either way, what you could do to improve your possibilities to get a good job in this. You're already doing geoscience studies, so that's necessary. Undergraduates is fine. You have to be a bit of an all-rounder in all geology, so you need to have good basic understanding of geochemistry, petrology, structural geology. Bit of geophysics doesn't hurt. Field work is useful, but if you can't do field work, there's still roles, lots of roles that don't require you to do that. So it is not exclusive for being a field geologist. For example, these days, there are lots of exploration companies who use remote sensing, so computer-based work to enhance the exploration efforts. So you don't have to be a field-able geologist to do this stuff. But you have to have a little bit of an understanding of the basics. MSc can be beneficial. There is a good argument to be made that it's good to have one core skill, one strong skill, which you can then supplement with the other core basic things. So that is something to consider. Getting a relevant dissertation project obviously helps if you can get something that is somehow relevant potentially to mining exploration, environmental considerations, then that's of course helpful. Building up your CV with extracurricular activities, it's helpful anyway. I mean, regardless of whether you go into minerals or not, it's a good idea to just to show that you're an active and proactive person. But for us in particular, there are certainly lots of workshops and lectures online, especially these days, that you can participate. Or the Deposits Hub here is a good resource. They do both streaming and recorded lectures. They do workshops, so get engaged with them. Go to field trips if you can. Get internships, other relevant experience if you can, even if it's short or even unpaid if you're really keen. And if you can get to those conferences, there's something called Mineral Deposit Studies Group, which is a UK-based one. It's usually early January, but because of COVID, it got postponed this year, so you can still make it. But I don't think there's a date set for that yet, but I think there was talk that it would be in April, so watch this space. There's something called Roundup, which is in Vancouver, late January. And if you're really keen, that's a really good investment. It's not cheap. but there's loads of companies that go there, that hire, and you can talk to them. So it's a good investment if you're fairly certain this is what you want to do. Soft skills, and this is really important not only for oil exploration or minerals industry. If all companies want people with good soft skills, so team working is really important, especially in an exploration setting. You might be stuck somewhere really remote with a group of people for months. So you have to be just able to get on with people, and you have to be able to communicate with locals in a positive and constructive way. So that the companies are really looking for people like that. And communication skills, again, in any walk of life. If you have good written or presentation skills, that certainly will do you no harm. But yes, if you are now enthused by a potential oil's career, do check out the Society of Economic Geologists. Many universities have local student chapters who do field trips, workshops, etc. But there's certainly the parent organization. Student membership is $25 a year for that parent organization, and you get newsletters, networking and possibilities, etc. So it is really a no-brainer just to get active in that. That's all I really wanted to say, I think, and I'm right about on time as well. A couple of maybe key publications here, resources that you might want to look up. There's a couple of reports here about the role of minerals and metals in the energy transition. And if you want to have a look at what exploration entails in terms of steps and different methods and skill sets, there's a really good review in this SCG newsletter from 2019 that you can download from online. It's a good review of what you actually need to efficiently explore for deposits. And yeah, that's it for me. Thanks very much for listening. And questions, please.
Thank you, Taija. That was definitely a very important talk. Yeah, questions, put them in the chat if you got any. I see there's one actually already. Pete Burgess, really interesting talk. Thank you. A question: how do you think these mining company exploration budgets compare to estimated costs of all the various economic and human life losses likely due to anthropogenic climate change? If they are relatively small, is this a useful argument to increase them? E.g., we should pay a lot more to explore, develop new exploration methods, etc., because in the end, it'll be less expensive than the costs of less than 2-degree warming.
Yes, no, that's a good point. And it's an interesting scenario. Ideally, I would like to see, especially the advanced world, the economically advanced world, support these activities a bit more in the society. We can afford to support exploration, but there's a fine line between using taxpayers' money to help companies to make more profit. So it's a political balancing act. How do you do that? But I absolutely agree that if we don't do anything, the cost to both economic and human cost of climate change is going to be huge. So how are we going to enhance exploration so that we can actually meet the need for these resources is going to be the challenge of the century, if not one of the challenges of humankind. So yeah, there are no easy answers to this, but I absolutely agree with you.
Yeah, another question from Chris Gilsenan. What should governments be doing to apply regulation and directive on the mining and energy industries to move geosciences towards this change economically?
Well, there are lots of countries, especially in Western world, who have quite good, strong mining and environmental laws already. The UK environmental laws are good. Mining laws, unfortunately, are lagging behind what we actually need. So that's hampering exploration in the UK specifically. The legislation just simply isn't there to encourage investment in exploration in this country, unfortunately, because the process is really old-fashioned. It's the land ownership and the mineral rights ownership is really, really complicated, and it harks back to Victorian times. So it's not encouraging people to companies to invest in exploration in the UK in particular, and many other countries may well be in the same boat. So certainly, if I think about the UK government, there should be some serious changes to the mineral rights laws and to the exploration laws and licensing laws, alongside with the environmental laws as well. They have to be strong, of course, but you have to also then think about how you reconcile between the fact that it's better to produce these things in an industrial jurisdiction where the environmental laws are strong versus outsourcing them to Congo, wherever, who knows what's going on over there. So yeah, I would say in the UK, certainly there would be a lot to do in terms of how the legislation is currently drawn up with respect to these things.
Okay, thank you. Yeah, we've got another question. Leonardo Yuda, sorry if I've butchered that one. Very good talk. What other skills would you recommend students to invest in to stand out in this expanding field? In particular, the ones that would be required to meet the increasing demands, and especially for geophysicists, is there another SEG sort of group that they could join, or chapters, competitions, funding for conferences, etc.? Yeah.
Yes, so but exploration companies in particular, they are looking for people who demonstrate interest. Employment routes into ores and mining is quite different from lots of other industries. The positions are not necessarily advertised widely, so networking is really, really important. So if you want to stand out, if you want to really get into this game, you have to invest in networking, not necessarily so much money, but certainly time. So get involved in student chapters, online discussions, conferences, whatever you can, and just talk to people, talk to companies, because quite a lot of these jobs are word to mouth, and quite a lot of these jobs are just people knocking on doors of companies and just asking. So and if your name is out there and people know that you're a decent person and you're a team worker, then that really helps. And yes, there's the other SEG for geophysicists, which is slightly confusing. And yeah, so participating in both is not a bad thing, particularly if you're leaning towards geophysics, which is also a very useful skill in mining and exploration. So that is certainly something else you might want to consider.
Yeah, we've got another question from Matthew Bell. What regulations or incentives could the more developed countries give to developing countries to help them move towards a more sustainable, energy-orientated future?
More developed countries, well, I think they're already getting there, and hopefully quite a lot of them will be able to jump over this hydrocarbon dominated society a little bit. I mean, they are already sort of there, but I think if there could be some sort of incentive, a global, a Western world, if you like, what's the word? Sort of common approach to this, that we are going to have to help these countries build their own sustainable energy network. That would certainly be helpful, I'm sure, to encourage them to not use hydrocarbons. But that would require certainly a very concerted common approach, and I'm not sure how easy that is to achieve. I don't think there was anything like that even discussed at the COP26. There were discussions going on how we can support developing countries to build these resources and move away from hydrocarbons. But as any concrete actions, I think it's politically very difficult question again, how we're actually going to do that and what the incentives in practice would be. So yeah, again, very, very complicated questions with no easy answers. I certainly don't have one.
Thanks. Hopefully we've got time. I've got a small question actually. So I think as scientific advancements continue, the need for rare earth elements is going to increase more and more in ways that we wouldn't have expected. How would you even go about getting economic amounts of rare earth elements? Obviously, hence the name, they're quite rare.
Well, they're actually not that rare. They're just usually present in such a small amounts that they are not necessarily feasible to extract economically. So it's the same as with any other deposits and metal or mineral or element type. We just have to understand where these things occur and then direct our exploration efforts towards finding them. And for quite a lot of rare earths, they come as byproducts of other metal production. So also enhancing processing of those other metals so that we can actually just dump those valuable other elements that might be needed. That is taken into account in planning the processing, and it might not always be technically feasible, but certainly something that I think it could be looked into much more than it is currently as to how we can actually get the telluriums out of the gold deposit as well as the gold and silver itself, for example. So yeah, that's so certainly lots to do there in terms of technology and understanding the basic occurrence of these things.